Hello, in this video we are going to see how we can design a circular patch antenna for 2.4 GHz on FR4 substrate having thickness 1.6 mm. So these will be the main parameters that we have to calculate. First will be the radius, then the feed point and the feed gap and the feed width. So let's see that. So while designing the circular patch, the main thing is the radius. So the radius can be calculated using this equation. So you have to substitute the resonant frequency in hertz. You have to convert this into hertz and substitute it here. And after calculating the F, you can use this equation. For height, you can use the height in centimeter. So if you are not going to do the equation, there are some online calculators. I will show you which calculator we can use. So here I am using this online calculator. I will put the link in our description. And so I put the resonant frequency epsilon r as it is FR4. The epsilon r is 4.3, height is 1.6 mm. So if you compute, you will be getting the effective radius and the actual physical radius. So this physical radius that we have to use for the design. So I'll be using 17.1 for our design. So we have calculated the radius, and next step is to finding out this FP, that is the distance from the center to the feed point. So FP is usually 30 to 50% of the radius. So I have taken around 42% of A, that is 7.1. So I have optimized it as if I take 42% of A, I'll be getting good matching. So FP is I have taken as 42% of A, so FP is 7.1, and A minus FP is the this point from the edge of the circular patch, so it will be A minus FP. And this is the gap, so this gap I have taken as 1.5 mm, and the distance from the edge of this circle to this dielectric edge is 10 mm, and here it is 5 mm. And feed length I have taken around lambda by 4 here, and feed width it can be calculated using some online calculators, so I will show you. So here this tool I have used for calculating the feed width. So here I am going to use the dielectric constant 4.3 and height 1.6. So here you have to optimize the values to get an impedance of 50 ohm. So this is our feed. So so if I use 3.13 for a FR4 substrate having thickness 1.6 mm, I'll be getting an impedance of 50 ohm. So for different impedance, you can change these values and optimize it. So if you put different value, you will be getting different impedance. So 3.13 is the optimized value for this case. So I'm using that value here. So that feed width is 3.13 here. Okay. So these are the parameters that I'm going to use. So let's do the design in CST. Let's start new template, antennas, planar, time domain, and as the frequency of our interest is 2.4, we can select from 1 to 5, then click finish. First of all, I'm going to model the circle. So I'm going to take this thing. So it is circle, inner radius 0, outer radius A, and X center and Y center I have taken as 0, and as it is on the top of the patch I have taken H, thickness of the dielectric as H, and I'm going to give some thickness to this PEC. So the material is PEC. So let's preview. A is we have calculated the radius as 17.1, then H is 1.6 mm, which is the thickness of the dielectric. So we have the circular patch. So the next thing we have to do is we have to make this cut. So this cut, if we have a rectangle, it has to be start from minus A to this point, which will be having a length of A minus FP. And the width has to be include this feed width plus gap. So let's do that. So next step is we have to draw a rectangle. So this is actually the gap. So in X minimum, it has to be minus feed width by 2 minus gap and feed width by 2 plus gap. And this Y minimum, it is from minus A to minus A. Okay, minus A plus, because we have seen that the length is A minus FP. So we can go for A minus FP and just click preview. Feed width we have calculated as 3.1 and gap is 1.5 and FP is 7.1. Okay. So what is the, so it has to be from minus A plus, oh, it is on the back. Okay, so I have to provide some thickness, means as it is on the top of the patch, I have to give this value. So where calculation were correct, minus A plus A minus FP. So this was correct. So let's preview. So now it is selected on top of the patch. Okay, so now our aim is to, we have to remove that gap from the circle. So I have removed it, and now our aim is to draw the feed line so that we can do. So this is the feed and it has a width of 3.1 and it has to be from this point, that is minus A plus A minus FP to this position. So that is, we have a feed length we have taken as minus 14.75. So this is also on the top of the dielectric. So I have to give H plus 0.035. So let's preview. Oh, why? Oh, it has to be minus A minus FL because this feed length is calculated from this end. So I will show you. So this is the feed length. So it has to be from this point. This point, it is FL. So it has to be A plus FL. That's why we are getting some. Okay, so now it is okay. So now we have the feed. Now what we are going to do is we are going to draw the dielectric. So this is the dielectric. So in x-axis we have seen that the dielectric has to be an extension of 10 from this edge, and for y-axis it has to be 5. So let's do that. So for the x minimum, it is from this point, that is A plus 10, and on that, oh sorry, mine here, A minus A minus 10, and this portion A plus 10. And here it has to be from this point to a plus 5. So y max is a plus 5 and y minimum is minus a minus fl, and this is the dielectric, so 0 to h, and we have to use FR4 for low C. So let's preview. Okay, so it's okay. So now we have to draw the ground also. So I'm going to use the same dimension as the dielectric. So x minimum is minus a minus 10, a plus 10, y minimum is minus a minus fl, 2y maximum is a plus 5, and it is on the ground plane, that is 0. So this is PC, so it is on the ground. So we have the ground, patch, and the dielectric. So our next step is we have to provide the port. So zoom it and press F. Then if you press F, you can select the face. Otherwise, if you can go to pick and pick face. If you select this also, you can select the face. So I'm going to select this port. So if you double click, it will be selected, and what I'm going to do is I have to assign the port. So port, so we can use the calculate port extension coefficient here. So it will be taking the values from the selector face, that is 3.1 and 1.6 mm. So one thing you can do is you can calculate this extension coefficient and manually plot that port. Otherwise, you can construct the port. So it will be constructing the port. So now we have the port. Next thing is we have to just check the boundaries as open add space, and then I think everything is okay. You can start the simulation. So if you want to have the good accuracy of this result, what you can do is you can uh, increase this mesh settings, so then you will be getting more accurate results. Then if you start the simulation, the simulations will be started. So let's do that. So here you can see that the simulation is complete. We can go to the S parameter. Here you can see that we are having the good resonance at 2.46 gigahertz. So now we have designed a circular patch antenna having the resonance at 2.4 gigahertz. And now what we can do is we can go for the field monitors, and we can set the electric field and magnetic field for 2.46. Oh, sorry, 2.4. Okay, so as I need only for the structure bounding box, we can select this thing. So apply. So for the electric field also I'm going to use the same thing. And next is Farfiled. So for Farfiled we won't be able to use the subvolume as it is for the entire domain. So has to be for the entire domain, and click OK. So we have the electric field, magnetic field, and far field. Then if you start simulation, you will be getting. Okay, simulation is complete. So let's check the far field. So here you can see the far field. So if you show the structure and far field is transparent, you can see that how the far field is obtained. Here you can see that the far field is in the broadside, so that is, it is the main is so the main beam is perpendicular to the axis of the patch, so it is broad. So here you can see that the directivity is 6.12. We have to select actually the realized gain. So here you can see that the gain of the antenna is very low because we are using a low C dielectric FR4. So if you want to improve the gain of the antenna, one thing you can do is you can always select low loss dielectric like Rogers RT-Durite substrate. So next we are going to see how the like how the electric field distribution is happening. So I'm disabling these things. So let's see, select view front. So I want to see how the electric field distribution is happening here. So this is, as my CST crashed, I saved the file and reopened again. So here we can check the surface current first. So as we have to check the surface current on the patch, let's select this thing. So I have just grouped both this radiating patch and the field. So let's see the electric field, sorry, surface current first. So here you can see that how the surface current is varying. So if you drag it here, you can see that the surface current is minimum at the edges where the radiating slots comes, and it is maximum at the center. So if you animate the field, you can see that after how the surface current distribution is happening. You can see a circular distribution. This is why we have a Bessel function to evaluate the electric field. So let's see the electric field distribution on the patches. So as I have to see the electric field distribution on the patches, I'm going to give a cut plane showing that value. So 1.635 shows the electric field on top of the patches. So here you can see that the electric field is fringing at the ends. So to see that, you can use the cutting plane along the X or Y direction. So let's see the electric field along the Y direction, and here, so I'm going to drag this value to see the electric field more accurately. Here you can see that the fringing of the field, so it is the end of the patches. Here you can see how the fringing of the field is happening here. So this is why we have some effective aperture radius instead of the physical radius. Okay, so next. So this is the magnetic field distribution. So we have seen the surface current and the electric field distribution and the far field. So this is how the circular polarized patch antennas are simulated. I hope you get some ideas. Thank you.